Hello and welcome to the third in my series of videos talking about explaining explaining away a lot of the mysteries involved in modern day quantum physics. I hope you've seen my first two videos. One on Young's double slit experiment and then the next one on quantum entanglement, both of which makes understanding exactly what's happening there very, very simple. This third is obviously on the photoelectric effect, for which Einstein won his Nobel Prize. I always thought that was a bit of a travesty that he didn't get a Nobel Prize for relativity, but there you have it. And I will be revisiting the Young's double slit experiment in this short video. But first of all, let's just have a brief discussion on what photoelectric effect is. And we're just going to read a bit from Encyclopedia Britannica, which is a nice little explanation. In 1905, Einstein explained the photoelectric effect, which is the emission of electrons by a metal surface when it is irradiated by light or more energetic photons. The kinetic energy of the emitted electrons depends on the frequency of the radiation, not on its intensity. For a given metal, there is a threshold frequency below which no electrons are emitted. Furthermore, emission takes place as soon as the light shines on the surface. There is no detectable delay. Einstein showed that these results can be explained by two assumptions: that light is composed of corpuscles or photons, the energy of which is given by Planck's relationship, and two, that an atom in the metal can absorb either a whole photon or nothing. Part of the energy of the absorbed photon frees an electron. There it is. That's the explanation. He uses that old-fashioned word corpuscles or photons. Don't use that. It's a kind of thing that Isaac Newton might have used. It's a photon, a particle. This little diagram here, the thing that happens here, we've got a plate of potassium illustrated here. And we're shining different coloured lights on. So if we shine red coloured light that has a wavelength of 700 nanometers at 1.77 electron volts, then that doesn't have any effect on the potassium. Nothing happens. And the mystery was, back then, if we make this red light more intense, more intense, why did the potassium continue to ignore it? And yet when you put a different coloured light, you applied a different coloured light, green or blue, then you got this effect of electrons shifting along. It's not quite as simple as this diagram makes it out to be. And quite simply, potassium has a threshold voltage, a threshold level of 2 electron volts, and the red light is coming in at 1.77 electron volts, so it never reaches that threshold value. And Einstein explained this as the particles of light, the photons of light, each in a packet, without the necessary energy to release these electrons. But when we apply more energetic light, green or blue, then green having coming in at 550 nanometers, an energy level of 2.25 electron volts. It's above the 2 electron volts needed to eject electrons, so therefore it happens. So it's as simple as that. It doesn't have any real mysteries involved. Let me just take all these marks out. It doesn't have any real mysteries involved, and in actual fact it's not quite as simple as this. Let me just show you how this would be done in practice. I've got an old-fashioned sort of circuit diagram here I can bring in, and this is an old-fashioned way, but this is essentially what happened. The bottom part of this circuit is here to hold the plates. This is our photo sensitive plate. This is our receiving plate in this evacuated quartz tube. So this bottom part of the circuit is there to hold this plate more negative than this plate, and nothing happens until the light comes in. And if we were working with potassium, it wouldn't work on red light, it would work on green or blue light. When the light comes in, then electrons would flow between the two plates, and you'd be able to measure the voltage across there, and the current would flow. That's it. There's no real mysteries involved. What was mysterious was, at the time, was why making this more intense had no effect. You're making a more intense light. Why isn't that? Why doesn't that have an effect? And Einstein came up with the idea that light was particulate, and that each particle then created this effect in the potassium. Now, if I just let me clean those marks off. I'm going to go back and revisit oh, hang on, let me take that one out. I'm going to revisit the double slit experiment. There we have the light source coming through the first slit in waves and separated in the second lot of slits to two slits, the double slit experiment, one wave interfering with the other, then we get the interference pattern. What I've said, to make this work and to demystify all of this as to how this is working, and how when we put any detector into the system at any point we lose the interference pattern, all of that is explained by the fact that photons here never had independent existence. All that happened is an individual an individual atom is excited here. Lots of individual atoms will be excited in this light source, but they're all excited, and they're not reacting to each other because they're all at the same excitation level. So each one is independently setting up its own wave system. So this is a map of a single atom through here, and it will make a single atom response here, single atom to single atom. That's it, as simple as that. And the randomness, when you turn this light source down so that only one single atom at a time is excited, the randomness of where it appears on here is just the randomness of what it appears on the screen. It's just the randomness of the availability of the atoms over here at the time. It could be any of these atoms. It's random, but if you leave it on long enough, of course it's going to build up into into the interference pattern. So what we saw was this: there was no independent particle acting across here. It's just this atom reacting with the mother atom, sending out a signal to the receiver atom. That's it. So that, as I said, when we turn it down, you can see this happening a single piece at a time. Now, if we had, I'm just going to fade that away and bring this one back in. So if we had this realization at the time that this light source, this red light source here, is a single atom trying to communicate, trying to transfer its extra energy into a single atom down here. However, this single atom in potassium is already excited with respect to this one. It's already at an excitation level. It's already at 2 electron volts. This single atom is excited to 1.77 electron volts. The potassium is not going to take any notice of it. A potassium atom is not going to see that. It's not going to take on extra energy because it's not being given any extra energy. It's as simple as that. Single atom to single atom. So when we excite the atoms even more, so that the color changes, so that each atom is so this atom is now at 550. Its wavelength signal is at 550 nanometers at 2.25 electron volts. Yes, now that this atom is now under the energy level of that atom, so energy takes place, and because of the nature of the potassium, then the photoelectric effect happens. The only thing we need to discuss further in that, I mean, the whole thing's very simple. The only thing we need to discuss further in that is that we have this photon effect coming here, and then this electron movement effect. Photon, electron, what's the difference? What are they? What is a photon? What is an electron? I'm going to produce my next video soon, video 4, and it's going to be on just that. It's going to be on exactly what a photon and electron, what exactly photons and electrons are, plus the Pauli exclusion principle and anything else that comes up in that discussion. So thank you for being here, and I hope you'll be with me on the next one. Goodbye.